Strychnine is a white, odorless, bitter crystalline powder used as a pesticide to kill rats and used to be used to kill moles till it was banned by the European Union. Historically, it was used as a poison and as a treatment to a range of ailments when taken in a diluted tablet form. These medicinal practices were generally homeopathic and so had very little reliability and did not end up treating what they were prescribed for, and occasionally could end up producing more of a problem than they would solve. Originally, the synthesis included processing the Strychnos nux vomica tree bark and seeds. However, strychnine is now synthesized through a complex route known as Woodward synthesis. Currently, many other variations of this route exist, as strychnine has a complex cyclical structure as shown in the poster. And so there will be multiple ways to synthesize it with different yields and effectivenesses and time it would take to do so. However, Woodward synthesis is the basis for most of these. Strychnine has a molecular weight of 334.42 grams per mole and is toxic and harmful to the environment, so it must be treated with care within a laboratory. It has a melting point of approximately 284 to 286 degrees Celsius and is slightly soluble in water, but completely soluble in chloroform and hot ethanol, yet is insoluble in diethyl ether. Strychnine is stable under the recommended storage conditions, which are generally just keeping it in a safe, sealed container, labelled and out of reach of children, but in a lab you would expect children not to be in there anyway, so yeah. The pharmacokinetics, the Cmax is demonstrated within the table for varying concentrations of strychnine which were used in the experiment, where an intragastric method was used on rats. This method was used so that the rats would not risk crushing the capsules during the intake, and so it went directly into the gastric system, which allowed for analysis of strychnine concentration absorbed through the gastrointestinal tract, which is the most likely location of strychnine absorption. However, it should be noted that strychnine could be absorbed through the mucous membranes, the main one being the mouth, which was avoided in this method, which is a slight drawback. However, most absorption of strychnine is through the gastric system, and so the Cmax data is accurate enough to draw conclusions from, though I would assume most of the error margins are due to this and maybe practical issues. Under the mechanism, strychnine has many observable pharmacological mechanisms. The main contributing mechanism to the toxic effects of strychnine is the competitive inhibition of glycine receptors. Glycine receptors are ligand-gated ion channels commonly found throughout the body, specifically in large quantities in the spinal cord and brainstem, where they act as a receptor for glycine, which is a neurotransmitter, so is highly reliable for muscle communication throughout the body and contraction, so is reliable for your movement, hence why the poisoning of strychnine generally results in muscle cramping and so forth. Under metabolism, strychnine is quickly metabolized by the liver microsomal enzyme system, as demonstrated in vitro rabbit liver as sourced. The enzymes produce 5 main metabolites identified as 2-hydroxystrychnine, 11,12-dehydrostrychnine, strychnine 21,22 epoxide, 21,22-dihydroxy-22-hydrostrychnine, and strychnine N-oxide, which make up 99% of all metabolites from this metabolism route, which is generally all of them, well, close enough. The observed metabolites were also observed in rat urine, not rabbit liver. However, in this case, the major metabolite was strychnine 21,22 epoxide, not strychnine N-oxide as found in the rabbit liver. This information is important to draw conclusions for the human metabolism of strychnine, as currently the metabolic produce in humans is not known. However, due to the similarity of rats and rabbits to humans, rats being more similar, a fair conclusion that these metabolites are most likely the ones in humans can be drawn. The toxic effects of strychnine poisoning, as mentioned before, include severe convulsions, muscle cramping, hyperflexia, and respiratory arrest due to hypoxemia, leading to death due to the respiratory system cramping up too much and causing the respiratory arrest. The LD50 of strychnine is approximately 30 milligrams per kilogram. The European Union, due to the high LD50 and further things, withdrew strychnine as a mold control substance in the EU Directive 91/414/EEC in 2006. Furthermore, the toxicity of strychnine was demonstrated in a case study showing a 28-year-old man who was admitted 2 hours after ingestion of 1 to 1.5 grams of strychnine. He appeared severely agitated and in mild respiratory distress. Blood pressure was 90/60. Pulse was 110 per minute, which is higher than average, and peripheral pulses were weak. He had generalized hyperactive reflexes and had several generalized tonic-clonic convulsions in the emergency department. Treatment consisted of gastric lavage with water, oral administration of activated charcoal and sorbitol solution, continuous intravenous administration of midazolam followed by sodium thiopental, furosemide, sodium bicarbonate, and hemodialysis for acute renal failure. His clinical course included respiratory distress, agitation, generalized tonic-clonic convulsions, and all the things mentioned earlier. He was able to recover within 23 days, which was impressive considering that he had consumed what would generally be expected as a fatal amount of strychnine. This suggests that with care and good support, a poisoned victim of strychnine still has the capability to recover, which is most likely why it's not seen as a poison today, though it is found occasionally laced within drugs, and so in autopsies it must always be checked to make sure that strychnine was not the cause of death if it is drug related, though it's still unlikely. Thank you for listening to this.